All right, so we've established that in order for a benzene to undergo an electrophilic aromatic substitution reaction, it needs to be reacted with a pretty strong electrophile. Okay, benzene acts as our nucleophile. We need a really strong electrophile because benzene's not that reactive. An alkyl halide, while it does have a polar bond between a carbon and a halogen, is not an effective nucleophile for an electrophilic aromatic substitution reaction. The carbon, like we said, is attached to a halogen, so it does have a bit of a partial positive charge due to the polar bond, but it's not nearly enough for the benzene ring to react with it. On the other hand, once again, in the presence of a Lewis acid catalyst, we can get an alkylation reaction. This is because the Lewis acid reacts with the alkyl halide to produce a very strong electrophile. In the first step, the alkyl halide reacts with the Lewis acid, and in this case, we see our Lewis acid is AlCl3, to form a carbocation. That's a carbon with a positive charge. The ring can then attack this very electrophilic carbon. So let's look at the mechanism, right? So we already know that a Lewis acid catalyst and an alkyl halide can react to form a carbocation. We saw that in the last slide. This is the electrophilic agent that the benzene ring will now attack. Once the double bond attacks that positively charged carbon, we create a carbocation intermediate. Okay. Once again, as with all of the carbocation intermediates we have seen produced in these types of reactions, this is stabilized by resonance. Okay. We have this sigma complex that is stabilized by resonance. And then finally, in the last step, the AlCl4 extracts a proton, having a chloride ion take the proton from the carbon where the alkyl group is now attached. This allows those electrons to go back into the ring and aromaticity is restored. Since we form a carbocation, we can get something called carbocation rearrangements. That means that this is not a useful reaction to use with primary alkyl halides. Okay, this would produce primary carbocations that would then rearrange to form more stable secondary or tertiary carbocations. So we cannot do this reaction with primary carbocations or primary alkyl halides. The alkyl halide Lewis acid complex can undergo something called a hydride shift, right? This would cause a primary carbocation to be changed into a more stable secondary carbocation, which the benzene ring would then react with. So we've already seen one major limitation of Friedel-Crafts alkylation, and that is that we cannot use primary alkyl halides in this reaction without getting what is called a carbocation rearrangement, right? There are three other major limitations to Friedel-Crafts alkylations. Number one, the halide group must be attached to an sp3 hybridized carbon. Okay, the reaction will not work if the halogen is attached to either an sp or an sp2 hybridized carbon. We won't get anything. Okay, this is because we cannot form a carbocation on an sp2 hybridized carbon or an sp hybridized carbon. Okay, we also have the problem of multiple alkylations occurring. Okay, we're going to discuss this a little bit later, but once this reaction happens once, it's likely to happen like on the molecule a couple of different times. It's raring to go. So that can be a little bit of a disadvantage if you only want this reaction to occur one time. Okay, lastly, some substituted aromatic rings, such as nitrobenzene, a benzene group that already has an NO2 group on it, are so deactivated or so inactive that we can't get this type of reaction to occur on those. Okay, we'll talk about this again a little bit later on.